Okay, next problem, number 58. We're given an air-filled capacitor. We're told the voltage difference. We're given a surface charge density of 3 times 10 to the negative 10 coulombs per centimeter squared. So let's talk about surface charge density. Well, we have a charge over an area. So that's a surface, right? So the surface is going to give you an area. So charge over area, 3 times 10 to the negative 10 coulombs over 0.01 squared. This is your conversion factor to meters squared, right? And now we want to find the distance between the plates in the capacitor. Okay, so again, surface charge density is just charge over area. That's what we're given. And now what we can do is we can use our capacitance identities that we know, right? We know that capacitance is equal to these things. And so we're given V, we know V. We know Q over A. And we know epsilon naught. So that's enough to solve for D right there. So let's set this up. Epsilon naught A over D is equal to Q over V. Now let's do this. Epsilon naught over D is equal to Q over A 1 over V. This is our surface charge density. Look at that. So now we want to just solve for D, right? So we put D up top. And then we have, I'm just going to write it like this. This is inverted. Okay, this is inverted. Epsilon naught delta V. Let me just double check this. So we put let's just D over here, put A over Q here, times V times epsilon naught. Yep, okay, good. Okay, so then we plug this in. We plug these values in. We have all of these values. Remember, this is the surface charge density, so this is 1 over the surface charge density. I don't know, you can use some value, alpha, call it whatever you want to call it. This is surface charge density. 1 over surface charge density times epsilon naught times delta V equals D. That's going to equal, after plugging everything in, 4.43 times 10 to the negative 4 meters, or we could just say it's 0.44 millimeters. That's the distance between the plates, okay? Next problem, we're given a dielectric plate, parallel plate capacitor. We're given the dielectric constant. We're given, what's this? We're given dielectric field strength. So dielectric strength, otherwise the electric field strength, right? That's what we're given there. We know this because this is the unit of an electric field, and we want to find a desired. I didn't write that down right. So this is actually 0.25 microfarads. That's what we want to find. We want capacitance to equal that. And then we also want the potential difference to equal 4 kilovolts. So we're asked to find the minimum area of the capacitor plates. So, recall, we have this for dielectrics. This is in the summary. Okay? Now, we don't know what the distance is, right? But we do have another identity that we can use because we're given delta V is equal to D times E, right? So that means that D is equal to delta V over E. If we're just taking the magnitude, this is not really that important because the negative is going to imply a direction. Okay, but anyway, so let's plug this in. So now we're given this is a value of 3. Just double checking my work here. That's 3 times epsilon naught, which is 8.85. Sorry, 8.85 times 10 to the negative 12. And then we have area, which we're given. No, we are not given area. We're solving for area. Sorry, my bad. That's a mistake. So, sorry. Moving a little too quickly. So what we want to do is solve for area. So we have a desired capacitance. We go D times capacitance over the dielectric constant and epsilon naught. And again, I'm not sure why I decided to use... Oh, I'm replacing this. That's why. Okay, so this goes here. So now we have delta V over E. That we know. We know what E is. We know what E is because that's in units of volts per meter. Our dielectric strength is our field strength. So what I'm going to do is plug all of this in. 4 times 10 to the 3 volts over 2 times 10 to the 8, 2 times 10 to the 8 volts per meter, times, what do we have here? K was 3, 1 over 3, 1 over epsilon naught, 8.85 times 10 to the negative 12. And we have the units there. I wrote them up earlier. You can look this up just about anywhere. This value, I mean. And then, is that everything? Let's see. C, no, we're missing capacitance, which is going to be 4 times 10 to the... Nope, that's wrong. It's actually going to be 0.25 times 10 to the negative 6 farads. There we go. Okay. There we go. Giving these discussions is really weird because I'm just talking to myself, so it's like not interactive. It's a little strange. So anyhow, I plug all of this in and I get 0.188 square meters, okay? And I went through and checked all of the units. I recommend you do the same. Volts over volts, right? Then we have farads over farads. There was one here. It comes from here. Meters, farads, meters. That actually comes out of the epsilon naught. So there's a couple of ways you can define those units. Meters, and then, yeah, so this is going to be meters times meters, and that's meters squared. Good, we're good. Cool.